So welcome to the Winds and Currents webinar. And today we have Jörn Callies, who's going to talk about geostrophic turbulence and near-inertial waves in the upper ocean. And I'll let you take it away, Jörn.
Okay, yeah, thanks for giving me the opportunity to speak here. I want to give a perspective on what we might be able to observe and what physics we might be able to learn with surface current observations from space. And so I'm gonna give it a little bit of a perspective, and I'm going to show some preliminary work that I've been doing with Scott Kahn, who's a graduate student here at Caltech. So if I was asked to sort of highlight the two major breakthroughs that altimetry, satellite altimetry, has afforded us. I would put up these two. One is it really gave us a global picture of the mesoscale eddy field. Right, we had an idea of their presence and their dynamics ever since the mode experiment, but satellite altimetry really gave us this global view of the largest reservoir of kinetic energy in the ocean. And then the other one, I would say, is tides, right? And both giving us tight constraints on the barotropic tide, but maybe more importantly, allowing us to understand the interaction between the barotropic and the baroclinic tide. Putting up here this famous plot from Ray and Mitchum, who showed the conversion of the barotropic tide to the internal tide at the Hawaiian Ridge and the propagation away from the Hawaiian Ridge.
Jörn, can I suggest that you shrink the panel of people because that's showing up on the shared screen?
Oh, I see.
That's perfect.
Okay, thanks. Okay, so that had large implications for understanding of the tides, of the Earth-Moon system evolution, of deep mixing in the ocean, and so satellite altimetry really was a major advance there. But there are things that are missing in our satellite altimetry record, and I guess the guiding question, as I said, of this talk is going to be what might Odyssey reveal that we have been missing with satellite altimetry. And so one is smaller scales, right? Geostrophic motions at scales smaller than what we can resolve with a satellite altimetry. We typically call the sub-mesoscales. This is a snapshot from a numerical simulation that we've run in my group. You can see the Gulf Stream running along here, shedding mesoscale eddies, 100-kilometer scale eddies. But then you see this complicated web of currents at smaller scales, fronts, filaments, sub-mesoscale motion that evolve rapidly in time at scales much smaller than what we can capture with a satellite altimetry. And so I don't want to belabor the importance of these sub-mesoscales, but they're thought to be important in the vertical exchange of traces between the surface and the interior of the ocean. They exchange energy both ways with a mesoscale. They might drain energy to small scales, and they might be important for setting the community structure in the upper ocean. I want to point out one feature of submesoscale, geostrophic submesoscale turbulence that I think is important to keep in mind, and this will be obvious to some of you, but I think it's worth reiterating, which is to do with the observability in different quantities, right? And so with SWAT, we're trying to observe the submesoscales, or as much of it as possible, and sea surface height. But that's challenging because the variance drops off very rapidly as we go to smaller scales. And so I'm illustrating that here with sort of a model spectrum of what the sea surface height spectrum due to geostrophic motions we think looks like. It falls off like k to the -4 in sea surface height variance. In other words, in this plan view of sea surface height, we're dealing with a very smooth field of sea surface elevation. And so if you want to push to smaller scales, you have to lower your noise floor quite substantially, right? For k to the -4, if you want to gain an order of magnitude in resolved scales, you have to lower the noise floor by 4 orders of magnitude. Okay, so that's pretty challenging. With surface velocities, you're in much better shape, right? Because sea surface height and velocities are related through geostrophic balance. There's a derivative, and so the k to the -4 turns into k to the -2 for kinetic energy. And so it's not as punishing to go to smaller scales, and so you don't have to reduce your noise floor as much to resolve finer and finer scales. You can sort of see that in these images of surface velocities. And the other major thing, and this is going to be mostly the topic of the rest of the talk, that we've been missing in altimetry is near-inertial waves. Okay, and that's because, not because they're weak, but because they don't have a leading order signal in sea surface height. Okay, and to see that, I want to give you a bit of a scaling argument, starting with the linearized equations of motion here. These are just the hydrostatic Boussinesq equations, linearized around a state at rest. And just looking at the first two equations, you sort of already see it, right? If you have an inertial oscillation, the balance is between the inertial terms and the Coriolis terms. The pressure terms are much smaller. But you can give a more quantitative argument with a scaling analysis. If you scale time with F, the horizontal scale with L, vertical scale with H, the velocity with U, then continuity tells you should scale W with H over LU. The buoyancy equation right here tells you that you should scale buoyancy with n squared times the scale of W, HL over U, divided by F. Okay, so that gives you the scale for buoyancy. And then hydrostatic balance gives you the scale for pressure. There's a factor H, n squared H squared over FL. Now you can write that as epsilon squared FLU, where epsilon is defined as NH over FL. Okay, so it's the ratio of the actual aspect ratio of your flow to the Prandtl ratio F over N. Okay, and for near-inertial waves, this is small. Okay, so for near-inertial waves, the aspect ratio is much smaller than the Prandtl ratio. The motion is mostly horizontal. You can see that from the dispersion relation. If you make a plane wave assumption, then if this ratio is small, the second term in the dispersion relation is much smaller than the first term, and the frequency is near F. Okay, now this epsilon squared shows up then in front of the pressure terms in the momentum equations, and so these pressure terms are smaller by a factor epsilon squared than the Coriolis terms. And so for the same velocities that would give you a pressure gradient, geostrophic pressure gradient, you get a reduced sea surface height signal by this factor epsilon squared for near-inertial waves. Okay, and so we haven't been seeing near-inertial waves in altimetry. And as I said, that's not because they're not strong, that's because they're dynamically filtered out. Okay, they are quite strong. They're a major reservoir of kinetic energy at the surface of the ocean. Showing here an example from a famous experiment led by Eric DeSaro in the Northeast Pacific. It's the STORMS experiment. Many of you have seen this figure. And these are drifter trajectories that drift along due to the geostrophic motion, the motion of mesoscale eddies. But then a storm hits and near-inertial waves get excited and they perform this clockwise spiraling motion. Okay, that is of comparable magnitude, if not larger, than the geostrophic velocities that are moving them along. You et al. Gave a nice overview of the kinetic energy reservoirs estimated from surface drifters. I'm picking out here two reservoirs, the low frequency, so that would be the mesoscale, and the near-inertial kinetic energy. And note that the color bars are different here, but I want to point out that there are major regions of the ocean where the near-inertial energy is as large, if not larger, than the mesoscale kinetic energy. So for example, the North Pacific here under the storm track, we have on the order of almost 10 to the minus 1 meter squared per second in the near-inertial band, whereas the kinetic energy is of the mesoscale is down close to 10 to the minus 2. Okay. But even in regions where they're comparable or where the mesoscale is on average more energetic than the near-inertial waves, we have to remember that near-inertial waves are highly intermittent, right? They're excited by passing storms. And so their velocities can still dominate for the few days after the passage of the storm, after the strong excitation of a near-inertial wave event. Okay, so at any point in time, we might still be strongly dominated by near-inertial waves. Okay, so for the rest of the presentation, I want to then make the case that these two compartments of the surface kinetic energy actually interact quite strongly. And so maybe that's not surprising that Navier-Stokes equations are nonlinear, and so everything interacts with everything. But I want to make the case that we can see this interaction in observations if we know what to look for. And we know what to look for because we have powerful theory to understand this interaction. Okay, I'm going to show you observations from the osmosis mooring array. So here is a figure by Christian Buckingham. This is the location of the mooring array. It's on the Porcupine abyssal plain. And it consists of these 9 moorings that are arranged in this pattern. I'm only going to show observations from these outer 4 moorings and the central mooring. And they're spaced at 13.5 kilometers. Okay, so they capture some of the mesoscale variability. So this experiment was really designed to understand submesoscales. Okay, and then what I'm showing on the bottom are time series of the wind over this mooring location. This is from Array 5, hourly winds for a subperiod. So these observations were collected for the duration of a year. Here we're just showing a couple of weeks where there's a strong wind event that excites near-inertial waves. Okay, you can see that event is right around here. It's not actually associated with very strong winds. It's associated with a rapid change in the direction of the wind. You can see in these wiggles here, and in the raw velocities from the central mooring. This is at 50 meters depth. You see the emergence of near-inertial waves. So before that, you have geostrophic currents as well as tidal currents. That's what's making up this variability here. But then around this time, the storm excites very strong near-inertial waves, and you can see that you have strong near F oscillations in both components of the velocity. Okay, so what we want to do is we want to understand these near-inertial waves and their evolution over the 2 weeks or so after the storm event. Okay, so the first tool that we have at our disposal to understand these near-inertial waves, and this has come up in the seminar series before, is a slab mixed layer model. Right? This goes back to Pollard and Millard. Very simply, you say my momentum equation simply consists of inertial terms, my inertial terms and my Coriolis terms, a forcing that is distributed over the mixed layer. And then you include an ad hoc damping term that represents the decay of these waves, mostly by propagation out of the mixed layer. Okay. Now we're going to reformulate this model by going to complex notation. So we're taking the first equation, adding I times the second equation, and we're going to describe the near-inertial waves in this complex form. It's quite convenient. U plus IV. And we can write that as that's a complex number. We can write that as a magnitude, well, a complex amplitude times e to the minus IFT. Okay, so near-inertial waves are rotating clockwise at the Coriolis frequency, and so this e to the minus IFT is taking care of that this purely inertial oscillation, and then the amplitude here, which I'll write as dz of m for reasons that will become clear later, that's a complex number that takes care of both the scaling, the magnitude of the near-inertial waves, as well as slow phase drifts, right? Changes in the phase relative to this pure inertial oscillation. Okay, if you write it this way, then our slab mixed layer model simply takes its form. dt of this complex magnitude equals the forcing, which is again the complexified version of the forcing, minus r times its magnitude. Okay, so that's just the damping. Okay, so we can take this model and run it for our storm event, right? We can take our wind forcing and plug it in, and then choose different values of r to represent the damping. Okay, so that's what's shown here. So these are, again, the same two panels as you've seen, the winds and the currents that we observe. Now we turn these observations into this language of complex near-inertial waves. And so we back rotate these observations, we filter them around the inertial peak, and we back rotate with this factor e to the IFT. And then we plot here the magnitude, right? This is the magnitude of DZM and the phase of DZM, okay? And so we see that, as I said, these waves are excited around 1016. They have a magnitude of around about 0.25 meters per second, and then they slowly decay over time. Okay, and then once they're excited, they have this slow phase drift that's shown in the phase over here. Okay, so then what's shown in the colored lines is the Pollard and Millard model, the slab mixed layer model, for different values of the damping, right? And you can see that while you sort of get some of the evolution, right? You get the excitation of near-inertial waves. That's great. But then no matter what value of R you pick, you get the decay that doesn't match the observations, right? If you have too small a damping, you get too high a peak, and then the decay is still too fast. Or if you have larger damping, you get the peak right, but you have almost no magnitude left pretty soon after the event. Okay, and the phase evolution is actually in the wrong direction, right? The phase evolves in the wrong direction compared to the observations. Okay, so what we want to do is we want to try to understand whether the presence of mesoscales has something to do with this mismatch between the slab mixed layer model and the observations. Okay, so these waves are, of course, excited in the presence of mesoscale eddies, and I'm showing you here a snapshot of the vorticity derived from satellite altimetry. Right, it's just taking the altimetry maps and deriving the vorticity, and this is our mooring array here. And now we want to ask, how does the presence of the mesoscale flow affect the evolution of near-inertial waves at this location of the mooring array? Okay, so essentially what we want to do is we want to solve the linearized wave evolution, where we now impose a mean flow, capital U, a geostrophic mean flow that both advects the waves as well as gets emitted around by the wave field. Okay, I'll simplify this here by assuming that the mean flow is barotropic, but that can be relaxed. Okay, now this looks quite complicated, but Young and Ben-Jalil told us how to reduce this system of a wave propagating in the presence of a mesoscale eddy field to a single equation that we can actually understand. Okay, so this is an equation for the slow evolution of near-inertial waves, very similar in spirit to the equation that I derived from the slab mixed layer model, right? It's an evolution for this complex magnitude dz of m. There's an additional z derivative here. And it evolves due to forcing, right? Just like before, there's forcing exciting near-inertial waves. We got rid of the damping because it was unphysical. But now there are three additional terms, right? And they have direct physical meaning, right? So the first term here is the advection of the near-inertial wave field by the geostrophic flow, right? So the geostrophic flow is represented by the geostrophic stream function psi. And so this is the Jacobian operator in the normal form. It's just advecting around the near-inertial wave field. This is the dispersion term. So if the wave has some horizontal structure, it will propagate around both in the horizontal and the vertical, and that's represented by this dispersion term. That happens whenever the wave frequency is slightly offset from f. Okay, and then there's a refraction term, right? And that's telling us that the phase is shifted whenever there's a vorticity in the geostrophic flow. Okay, so the del squared psi here is the geostrophic vorticity, what I showed you in the previous slide. Okay, Now, the assumptions here are that there's a timescale separation, right? That's quite a reasonable assumption. Near-inertial waves have a timescale near f. That's much faster than the evolution timescale for the geostrophic flow. Here, I'm assuming the geostrophic flow to be paratropic. That's reasonable over the upper couple hundred meters, but that can be relaxed. And I'm also assuming an f-plane here. That also can be relaxed. Okay, so now what we're going to do is we're going to take this equation, the YBJ equation, and we're going to, just like with the slab mixed layer model, we're going to force it with the observed winds. But now we're also going to put in this geostrophic stream function, psi, from altimetry. Okay, and so we're going to solve this in a three-dimensional domain for the evolution of M that tells us the evolution of the near-inertial wave field. Okay, so let me show you an animation of what that looks like. So here I'm going to show you a plan view of the near-inertial wave amplitude, right? The magnitude of mz. And then on the right, I'm showing you a cross section through the mooring array. This is x and z. So this is the surface, and this is 500 meters depth. Okay, so if I run this, I'm going to excite the near-inertial wave. This is by the winds, which we assume to be uniform over this domain, which is 400 by 400 kilometers. And then without eddies, this wave field would remain uniform in the horizontal. But you can see on the left that these waves assume structure imprinted by the mesoscale eddy field. And on the right, you see vertical propagation induced by that. Okay, and so now we can go back to our observations and try to see whether we can capture these observations better with this more complete description of the physics of near-inertial wave evolution in the presence of a mesoscale eddy field. And indeed, the simulations capture the evolution of the near-inertial wave field much better than the slab mixed layer model. Okay, even though, again, the forcing is exactly the same in these two cases. So that's what's shown here on the bottom. The top two panels you've seen before, that's a slab mixed layer model. On the bottom, we're showing the same thing, the amplitude on the left and the phase on the right. That's mislabeled here. This should be the phase, just like here. And so the dotted lines are, again, the observations. And here we're showing not just the central mooring, that's the black one, but also two other moorings, the one in the northeast, that's the red one here, and the one in the southwest, that's the blue one here. Okay, and then the solid lines are the simulations, and you can see that we capture the peak of the near-inertial wave amplitude much more reasonably than the slab mixed layer model. And I should say there's no tuning here, right? There's no damping factor R that we can adjust. The simulation manages to capture that peak quite well. And then it also captures more or less much better than the slab mixed layer model, the subsequent evolution at the location of the moorings, this sort of slow decay of the near-inertial wave amplitude, and this drift in phase in the positive direction at all of these moorings. And it captures some of the spatial variability across the mooring array, right? These are order 20 kilometers apart, the outer moorings. And so they sit in different parts of the mesoscale eddy field. And that is enough to give us quite different amplitudes of the near-inertial wave field at these moorings, as well as different evolutions over time. And the YBJ dynamics capture this evolution quite well. Okay. Now in these simulations, we've assumed that the eddy field is given. We have observations from altimetry, so we can use those observations to evolve our near-inertial wave field forward. But I want to at least mention that there's theory that allows us to understand the coupled evolution of the near-inertial wave field as well as the geostrophic flow. Okay, so this is theory that was developed by Shane Van Nest fairly recently, and it has a structure that is partly the same as the theory that I just showed you for the evolution of just the near-inertial waves, but now it has an evolution of a quasi-geostrophic flow as well. Okay, so again, here we have an evolution for M. This is now a more general form in which I'm allowing baroclinicity of the geostrophic flow. Okay, so there are more Z derivatives in various places here. But then what's important is that there's an evolution equation for the geostrophic flow. Okay, so there's a conservation statement of quasi-geostrophic potential vorticity that looks just like in normal QG, right? dtq equals the Jacobian of sine Q, where Q is the potential vorticity, and that has the normal term, the relative vorticity, and the stretching term. But now it is affected by the waves. Okay, so the presence of near-inertial waves has a potential vorticity associated with it. And that potential vorticity can be expressed in terms of this M, right? It's a complicated expression, but if we have an evolution equation for M, we can calculate what QW is, and we can invert this for psi, and then evolve forward the PV, just like in QG. Okay, so that allows us to understand the coupled evolution of near-inertial waves and the geostrophic flow. And that's quite important because that allows us to understand energy exchanges between the near-inertial wave field and the geostrophic eddies. Okay, they are not decoupled energetically either. They can exchange energy. And this was pointed out again by Shane Van Nest, and then Cesar Roca wrote a nice paper on this topic with Greg Wagner and Bill Young. And so what this theory tells us is that there are two conservation laws. One is for the wave kinetic energy, right? The near-inertial waves conserve their kinetic energy to leading order. But then there's an additional conservation law of the total energy, which consists of the geostrophic energy, which has a kinetic and a potential part. But then it also includes the wave potential energy. Okay, and so that conservation law tells us that there can be exchange between these compartments of energy, between wave potential energy and geostrophic total energy. Okay, and so if we think about the scenario of a storm exciting a near-inertial wave at large scales, right? If a wave has large scales, it has almost no potential energy. But then as this wave is refracted and advected around by the mesoscale eddy field, right, the structure of the mesoscale eddy field imprints itself on the near-inertial wave field. It gains potential energy, it gains horizontal structure, it gains potential energy, this term goes up. And so this conservation law tells us that that energy has to come from the geostrophic kinetic or potential energy. Okay, so this is termed stimulated generation. There's a generation of wave energy by the presence of geostrophic eddies, but it's not spontaneous. The geostrophic eddies don't spontaneously generate these waves. It's stimulated by the excitation by a storm. Okay, and so that's really all I have to say. And so to summarize, I want to say that again, observing submesoscales, submesoscale turbulence, the geostrophic turbulence at submesoscales, it's much easier in velocities than in surface height because there's more variance relative to what's at the mesoscale at the submesoscales. With altimetry, we've been mostly blind to near-inertial waves, even though they produce energetic surface currents that, especially after the passage of storms, often dominate the surface velocities, even in regions where the mesoscale eddy field is not particularly weak. And then, as I said, the evolution of near-inertial waves and geostrophic flow is intimately coupled. And we see this in observations, again, if we know what to look for, and we have powerful theory to know what to look for, right? Powerful theory that allows us to understand that entangled evolution of near-inertial waves and geostrophic flow. And so I think, thinking about Odyssey, this is really an opportunity to understand this entangled evolution of near-inertial waves and geostrophic flow in much more detail than is presently possible, because we have very little observations of the spatial structure of near-inertial waves. Right? I understand that there's an alias, there might be an aliasing issue with with satellite observations, right? We don't have a repeat that's hourly, but maybe we can come back to this in the discussion. But the evolution of the near-inertial wave field is quite slow, right? As soon as you take out the e to the IFT, the evolution of the magnitude and the phase is not that rapid. And so even with an aliased observation from space, I think we can understand this evolution quite well, again, if we have theory to guide that interpretation. So that's what I have. I have no idea what time it is, but happy to take questions.
Thanks very much, Jörn. Your timing's perfect. And yeah, the floor is open for questions. So please raise your hand or put questions in the chat. And maybe to start things off, I'll ask about one of the particularly interesting and exciting aspects of Odyssey, but also potentially complex for what you're thinking about, that in measuring winds and currents together, we imagine that winds are responding to currents and that they are imprinted with some of the structure of the currents. So that moves away from this sort of traditional model of uniform winds driving an ocean with mesoscale eddies to something with non-uniform winds driving non-uniform ocean.
Sure.
Any thoughts on how one might begin to address that?
Yeah, my feeling is that is important, and it has important effects, right? For example, for the evolution of the eddy field, the top drag that exerts. That's an important term in the energy budget of mesoscale eddies. But if you think about the stress that's exerted, it's still a second order correction to the stress that you get if you forget about the currents. And so I think to leading order that picture of a large scale storm putting in energy to the ocean bed will still hold. But yeah, there are important corrections to that, and I think that will be interesting to look for as well. And that's something that can be incorporated into these frameworks without a problem.
Yeah, as you say, it's a second order effect. I wonder if there's room to play with some of that theory.
Yeah, for sure. There's no reason not to include that, right? The forcing term allows you to make that dependent on the currents. So yeah, definitely that's possible.
I see that Dudley has his hand up.
Hi, Jörn. Thanks for the really nice presentation that even an observationalist like me can understand, more or less. Got a comment that I want to make on your first bullet point on this last slide here. Not sure that I totally agree that observing submesoscale velocities is easier than measuring submesoscale surface height variations. I understand your point, with the steep roll off of the wave number spectrum and stuff, but measuring velocity is not all that easy. It's a tricky thing, and it's contaminated by a lot of different things. And I would, based on the analysis that I did that you know about in that paper a couple of years ago, I'd say they're comparable. It sort of depends on what can be achieved engineering wise in terms of velocity measurement accuracy. But I think a key point to keep in mind that actually supports all that you're doing here is that something like Doppler scat measures the total velocity, not just the inferred geostrophic velocity from the surface height. So that's covered in part by your comment that it's blind to near-inertial waves, but there are other, non-geostrophic parts of the velocity field that would be missed by altimetry too. So in that sense, I agree with you. The velocity is preferable to sea surface height. But as stated in that first bullet, not sure I totally agree.
Yeah, it's a reduced statement. So it's your point is absolutely well taken. And I just wanted to make this point about going to small scales is easier. Once you observe the mesoscale and velocities, it's easier to go to small scales in velocity observations and in surface height. I'm completely casting away the technological considerations of what's easier to do. Right. So yeah, absolutely. Well,
I remember a conversation I had with Jim McWilliams about, oh gosh, it must have been 10 years ago now or something. It was at an ocean sciences meeting, and I had first noticed that with that steep roll off of the wave number spectrum, that to measure sub-mesoscale variability by altimetry, you'd have to get, a fraction of a centimeter accuracy. and I remember saying to Jim, I'm not sure we can really do that. And, Jim being the theoretician and stuff, he just smiled.
Yeah, and I think this is something that we'll see in SWOT observations, and I think we'll see a very strong internal tide signal in SWOT observations, in part because of this steep roll off. We'll capture some of the geostrophic submesoscales, but the tides don't fall off that steeply, and so we'll see a lot of tides.
Okay, thank you.
There's a exchange starting in the chat, and maybe Fabrice, do you want to unmute and ask your question?
Yeah, well, thanks. That's a very nice talk. I'm not sure it's a really question, but I was trying to wrap my head around the idea that, we know we're going to get this aliasing of near-inertial oscillations, and has been bugging us, especially with previous concept that had the narrower SWOT than Odyssey. And I was wondering if you look at specific dynamics for given latitudes and what kind of scales we get. Of course, you were looking at this example with osmosis, which is 48 or whatever degrees. Are things getting easier to separate as we go towards the equator, or it's not something that you ask yourself? Just thinking out loud.
You mean in terms of the aliasing? You have
the magnitude of the imprint of the quasi-geostrophic dynamics on the near-inertial oscillation. That's something which is stronger at higher latitudes or lower latitudes, or you get the same kind of ratio of energy between the two, or it's just because you don't get the same forcing as maybe in the low latitudes. I don't know, just trying to figure out what's going on here.
Yeah, the ratio of energies varies a lot, right? And that's because the ratio of both energies varies a lot geographically for different reasons, right? You have western boundary currents in the ACC where you have strong mesoscale eddies, and then you have storm tracks that excite near-inertial waves, and so they partially coincide, but both these fields will have strong regional variations by orders of magnitude, and so yeah, it varies very strongly geographically where you are, how strong these velocities are in relation to one another. The latitudinal variation of F is interesting, right? Because with tides, you can design an orbit and you can design a repeat period to have an alias that's acceptable, an alias period that's acceptable. With near-inertial waves, you sort of pick your latitude and get a reasonable alias period, but that will change depending on where you look. And so that's I think something one should probably think about.
And tides are also phase locked, or the parts we get out. So you can get the phase locked part of the tide out of a very slow repeat just by trusting the tide to be well behaved. But near-inertial oscillations are a different game.
Right, but there are components of the internal tide that have slow phase evolution as well, just like near-inertial waves. And so, I think similar ideas. I think Clément had a very nice way of thinking about this, applying an inverse method with a particular correlation structure that is near F or near the tides. And I think these ideas should be quite successful to extract these signals.
So Melanie's pointed out that the overlap of SWOTs at higher latitudes will provide higher frequency sampling than at low latitudes. So
yeah, that's a good point. So the frequency goes up as well. So probably the more rapid repeat still wins out. So there's probably more that one can do at high latitudes. That's
thinking about the contest between sorry, I didn't mean to speak over you. Thanks for a nice talk. I was thinking about whether the Rossby radius will get too small for our truly resolved scales of motions in the proposed Odyssey data by the time we get to the region of overlapping swaths. I'm not sure.
Yeah, somebody else will know the answer to this much better than I do, but the scale of the near-inertial wave variations will be the same as the mesoscale. It's the interaction with the mesoscale that produces these structures in the near-inertial wave field to leading order. And so, yeah, the Rossby radius goes down, but we typically still resolve mesoscale ADC in the tight latitudes.
And Jonathan Gula has a question in the chat. Do you want to unmute and ask?
Oh yeah, sure. I mean, thanks, Jörn, for the talk. I was just a basic question. Maybe you said it in the slides. I was just wondering if energetically the adding the mesoscale was a big difference in terms of energy injected. If you just look at the windwork or energy radiated downward as near-inertial waves, and if it's closer to the observed energy flux you can see with the osmosis data.
Yeah, we're in the energetics. Definitely the radiating downwards, right? I mean, in the SLAP model, there's no radiation downwards, sort of parameterized with the drag, but that's fake. It's just put in. With the YBJ dynamics, you do get essentially the inertial chimney effect, right? You refract into anticyclones, and then the wave dispersion makes the waves propagate downwards, and so there is propagation downwards. We started to look at the energetics. We also started to look at deeper current meters, and we seem to be capturing the bulk of the vertical propagation of these near-inertial wave fields. So we're quite confident that we're basically getting the energetics right as well, the flux of energies around.
Great, thanks.
Other questions? I'm wondering if we might come back to the aliasing question.
Sure.
And so satellite sampling twice a day at best, and then so which means that the near-inertial signal is pretty well aliased, as you noted. But and you said if you repeat enough times, you may be able to extract something. And I'm wondering what the effect of intermittent storms is on that. So does it matter how often a storm comes through and how persistent a near-inertial cycle is? And is there a way to put a time scale on that?
Yeah, so I guess I can only talk to the specific examples. We have a few more from this year-long record. The timescale of evolution seems to be mostly pretty consistent between them. It's on the order of, a few days, I would say. And so, yeah, the fastest evolution is when the storm passes, right? The storm is fast, and that's almost an impulsive forcing. But we have pretty good constraints on the storm, so that probably is okay. And then the evolution is on the time scale of a few days, right? The phase here as well. We see that pretty consistently across different events in the year-long record. So yeah, I mean, if you have a repeat of half a day, you get many of these observations that will allow you to constrain the amplitude and the phase of the near-inertial signal. I guess one part in relation to Clément's talk, right, is that one should be careful with the spatial correlation. Right, the structure of the near-inertial wave field is large scale initially, but very quickly the mesoscale imprints itself, and so one should probably be a little bit cautious in picking the correlation scale in the horizontal to not smooth out the near-inertial wave field too much.
Yeah, that makes sense. Amala has asked an interesting question. Amala, do you want to unmute and ask it?
Yeah, sure. So I was just wondering whether drifter trajectories can be helpful when they're well resolved, but along with some measure of some mesoscale. Have you tried thinking about that?
Yeah, I think there's the drifters I think are a great resource, and I think there's more work to be done to try to see some of these interactions in drifter data. Right, there's some work that tries to associate near-inertial wave amplitudes with the vorticity of the mesoscale eddy field. the main challenge of the drifter observations is that they're point measurements, right? And so you don't get the spatial structure of the near-inertial wave field, which I think is the main thing that Odyssey would add here.
Yeah, thank you. Really nice talk.
Thanks.
Are there any further questions?
Actually, I do have a question. This is Melanie again. Am I remembering correctly that with the model you're showing right now, you don't have any damping term for the near-inertial waves?
Yeah, that's right.
It's interesting to me that it doesn't seem to need one. Why do you think that is?
Because the waves propagate down, right? So you refract into anticyclones, and then the waves propagate downwards, out of view of the mooring at 50 meters depth, which is just at the base of the mixed layer. And so you see in the deeper moorings, you see the wave amplitude go up later in both the simulations and the observations. And so you don't need to parameterize that propagation into the interior of the ocean because we capture it in the model.
Okay, thanks.
While we have that slide on board, Jörn, this is Amit Tandon. Thanks for a very nice talk. What's going on in the first couple of days in the model? The amplitude seems to be smaller than what the observations show. And then the rest of the ramping up, it captures very great.
Right. So that's because we run the simulation for just this window that's shown, and we start from rest. And so we have no near-inertial wave field in the beginning, and then the wave slowly ramps it up over time. We've also done simulations where we start with the observed amplitude. We're a little bit hesitant to do that because we have to prescribe a spatial structure. If we make it large scale, that's probably not realistic for an aged wave field. But it doesn't matter much. Once the storm hits, that excites its own wave field that's quite strong, that overwhelms anything that happens prior to that.
Thanks.
But yeah, good eye. That's definitely an artifact of how we're initializing the simulation.
Thanks.
And I should also say that the phase is not meaningful here in the beginning because the amplitude is very small. And so it's only when the amplitude is large that the phase becomes meaningful and matches observations.
Maybe to follow up on Melanie's and Amit's question, I'll ask about the sensitivity to initial stratification.
Yeah, so that's something that we were careful about. So here we're actually using stratification from the glider observations from osmosis that Andy Thompson collected. So yes, you need to have a realistic stratification that enters through the n squared to get the vertical propagation right. So yeah, we need to have the right mixed layer depth, and then we need to have the right stratification at the base of the mixed layer to get the evolution right.
So how right is right? I guess I'm wondering if all you have is Argo in a rough grid and satellite data, are you good enough?
My guess is yes, but that's speculation. One would have to try.
Yeah, a question for further study. Okay, well, I'll give one more call for further questions. And if there's nothing further, then a big round of applause for Jörn. This was a really great talk, really stimulating discussion, and I appreciate you taking the time to do this for all of us.
Thanks for having me, and thanks for the discussion. That's fun.